This is a microchip. At first glance, it looks simple. A small, flat piece of silicon. Something that fits easily in your hand. Something you barely notice inside your phone, your laptop, your car, your television. But when you zoom in, everything changes. What looks like a tiny square becomes a city. A nanoscopic metropolis. Skyscrapers made of silicon. Hundreds of layers stacked on top of each other. Hundreds of kilometers of microscopic wires connecting everything. A hidden world built atom by atom. And at the very bottom of this city are billions of tiny switches. Transistors. These are the smallest working parts of modern civilization. They are the ones and zeros of the digital world. Every message you send. Every video you watch. Every calculation your device performs. All of it depends on these tiny structures. Inside a chip, electrons race from transistor to transistor. They move through invisible highways at incredible speed. And the smaller those transistors are, the faster everything works. Shorter distances, less resistance, more power, more speed, more intelligence. For more than 50 years, engineers kept shrinking these transistors. Smaller every generation. More packed into the same space. Every 2 years, roughly twice as many. This pattern became known as Moore's law. Not because it was a law of nature, but because it seemed unstoppable, year after year, decade after decade. Computers got faster. Phones got smarter. Storage got cheaper. The digital world exploded. And humanity built its modern life on top of this trend. But around 2015, something changed. Progress slowed, then stalled, then nearly stopped. Engineers had reached a wall, a physical limit. A limit written into the behavior of light itself. And it looked like Moore's law was about to die. It might have ended there, if not for one machine. A machine so complex that for decades, most scientists believed it could never exist. A machine that costs hundreds of millions of dollars. A machine that pushes physics, engineering, and precision to their absolute limits. A machine that saved the future of computing. To understand how extraordinary this machine is, imagine this. You are shrunk down to the size of an ant. You are standing inside a metal canyon. In front of you, a tiny droplet of molten tin flies past at hundreds of kilometers per hour. It is smaller than a human blood cell. It moves faster than a race car. And you are holding a laser, not a toy laser. A laser powerful enough to melt metal instantly. Your task is to hit that droplet. Not once, not twice, but 3 times in less than 20 microseconds. And you must never miss. Not once, not ever. Now imagine doing this 50,000 times every second. That is what this machine does. It fires lasers at microscopic droplets with perfect accuracy. Over and over, day after day, year after year. It never misses. Inside the same machine are mirrors so smooth that they may be the most perfect surfaces humanity has ever created. If one of these mirrors were expanded to the size of the Earth, the largest bump on it would be thinner than a playing card. It can align layers of a chip with errors smaller than 5 atoms. 5 atoms. All while parts of the machine move at forces strong enough to crush most equipment. For 30 years, engineers said this was impossible. For 30 years, it was just a dream. And yet today, it exists. Only one company on Earth can build it. Only one supply chain can support it. And without it, modern computing would freeze in time. To understand why this matters, you have to understand how chips are made. It begins with sand. Silicon dioxide, one of the most common materials on Earth. That sand is purified until it is almost perfectly pure silicon. Then it is melted inside massive furnaces. At extreme temperatures, a small crystal is lowered into the molten silicon. Atoms attached to it, layer by layer, slowly growing, until a giant crystal forms. A single flawless structure. This crystal is sliced into thousands of thin wafers, each one polished until it reflects light like glass. Then each wafer is coated with a special chemical called photoresist, a material that changes when light touches it. Light passes through a pattern mask. It hits the wafer. Some areas weaken, some stay strong. The weakened parts are washed away, leaving behind a microscopic design. That design is etched into the silicon. Metal is deposited. Wires are formed. And the process repeats again and again and again, dozens of times, sometimes hundreds, each layer stacked with atomic precision. At the bottom are the transistors, the hardest part, the most fragile, the most complex. Above them are highways of metal, carrying power, carrying signals, connecting everything. By the end, a single wafer contains hundreds of chips, each one more powerful than entire rooms of computers from the past. But there is one step that matters more than all others. The step where light draws the pattern. Photolithography. This is where physics fights engineering. Because light does not behave like paint. It bends. It spreads. It interferes with itself. As patterns get smaller, the gaps approach the wavelength of light. And at that scale, light refuses to cooperate. It blurs. It overlaps. It creates noise. This is diffraction. It is unavoidable. Instead of fighting it, engineers learn to control it. They design masks so that interference creates the right pattern. They turned a limitation into a tool. But even that had limits. Lenses can only be so large. Angles can only grow so much. Eventually they hit a wall. So the only option left was to use shorter wavelengths, smaller waves, finer brushes. For years the industry used deep ultraviolet light, 193 nanometers. It worked. Until it didn't. By 2015 it was no longer enough. The features were too small. The errors too large. Moore's law was collapsing. And that is when an old radical idea returned. An idea born in the 1980s. What if we use X-rays? What if we use light so short, so energetic, that it can draw patterns only a few atoms wide? In theory, it would work. In practice, it seemed impossible. X-rays are absorbed by air, by glass, by lenses, by almost everything. They require a vacuum. They destroy materials. They refuse to be focused. For decades, scientists gave up, until one man refused to. Kinoshita, a Japanese researcher. He believed it could work. Even when nobody else did, he searched for a way. And one day he found it. A paper about special mirrors. Mirrors that could reflect X-rays. Not perfectly, not efficiently, but enough to begin. And that was the spark. The beginning of the most ambitious engineering project in modern history. When Kinoshita first presented his idea, most people did not believe him. Not because they disliked him. Not because they wanted him to fail. But because what he was proposing seemed to violate common sense. He was claiming that invisible, destructive X-ray light could be bent, focused, and controlled with mirrors. That it could be shaped with atomic precision. That it could be used to write patterns smaller than anything ever made before. To most physicists in the 1980s, this sounded like science fiction. At conferences, people listened politely. Then they dismissed it. Some thought his results were mistakes. Others thought they were exaggerations. Some openly mocked the idea. They called it unrealistic. They called it a fantasy. They called it a big fish story. Kinoshita was devastated. Years of work, years of failed experiments, years of persistence. And no one believed him. But his belief did not change. He knew what he had seen. He knew what his measurements showed. He knew the physics was real. So he kept working, quietly, patiently, slowly improving his mirrors, slowly refining his method, slowly pushing the limits. But even if the mirrors worked, there was another problem. X-ray light does not exist naturally on Earth in useful amounts. You cannot buy it. You cannot generate it easily. You cannot store it. To produce it, scientists had to build machines the size of buildings. Particle accelerators, synchrotrons, circular tunnels where electrons raced at near light speed. As they curved, they emitted X-rays. Powerful, unstable, expensive. These machines consumed enormous energy. They required teams of engineers just to keep running. If the power failed, everything stopped. Factories shut down. Production froze. No company could afford to rely on something so fragile. So even supporters admitted the idea was impractical. Even if it worked in a lab, it would never work in industry. But the biggest obstacle was still ahead. The mirrors. To focus X-rays, the mirrors had to be unimaginably smooth. Not smooth by human standards. Not smooth by microscope standards. Smooth by atomic standards. Every surface has bumps. Even polished glass. Even diamonds. Even the best mirrors. When light hits a rough surface, it scatters. It loses direction. It becomes useless. For visible light, tiny bumps are fine. But X-rays have wavelengths thousands of times smaller. For them, even a few atoms are mountains. A normal household mirror has bumps thousands of atoms high. For X-ray mirrors, the bumps had to be less than 3 atoms. 3 atoms. If one of these mirrors were expanded to the size of Germany, the largest bump would be about 1 millimeter high. That is the level of perfection required. No factory in the world could do this. No polishing technique existed. No measurement tool was accurate enough. No material science process was reliable enough. It was beyond technology, beyond budgets, beyond imagination. And yet Kinoshita did not quit. He believed someone, somewhere, would eventually solve it and help arrive from an unexpected place. Not from Silicon Valley, not from chip companies, not from universities, from a nuclear weapons laboratory. Across the Pacific, near San Francisco, sits Lawrence Livermore National Laboratory. It was created during the Cold War, funded by the US government to design nuclear bombs. Its scientists studied what happens inside stars, inside explosions, inside fusion reactions, inside extreme environments. One of their problems was X-rays. Nuclear reactions release enormous amounts of X-ray radiation. But for decades, scientists could not capture it properly. They could not focus it. They could not analyze it. They could not measure it accurately. Then they heard about multi-layer mirrors, thin layers of different materials, stacked atom by atom, designed to reflect specific wavelengths. It was exactly what they needed. So they invested. They built equipment. They hired experts. They experimented. One of the scientists leading this work was Andrew Harila. His team began developing better mirrors, more layers, more precision, better materials, better control. Year by year, the reflection improved from 1% to 3% to 5% to higher. Still far from perfect, but enough to prove it could scale. Slowly, quietly, across 2 continents, 2 communities were working toward the same goal. One driven by computing, one driven by national security, one in Japan, one in America. Neither knew how important the other would become. In the late 1980s and early 1990s, more groups joined. Universities, research institutes, government labs, small startups. They shared data, they shared failures, they shared breakthroughs. Progress was slow, painfully slow. Years passed with little visible improvement. Funding was cut, projects were canceled, teams disbanded, many gave up. They said Moore's law would simply end, that humanity had reached its limit, that physics had won. But a few groups refused to accept that. They believed that if the mirrors could be perfected, if the light could be stabilized, if the vacuum systems could be controlled, then everything else would follow. It was no longer a scientific problem. It was an engineering marathon, one that would take decades, one that would require thousands of specialists, one that would cost billions, one that would reshape geopolitics. Because whoever controlled this technology would control computing, and whoever controlled computing would control the future. And slowly, almost invisibly, the impossible began to become possible. By the late 1990s, the dream of using extreme ultraviolet light had not disappeared. It had gone underground, into research labs, into classified facilities, into long-term projects few people talked about. Most companies had decided it was too risky, too expensive, too slow, too uncertain. They chose safer paths. They improved existing technology. They squeezed every last bit of performance out of old methods. They delayed the future. But one company chose a different path, a small Dutch firm called ASML. At the time, almost nobody outside the industry had heard of it. It was not a giant. It was not dominant. It did not have unlimited money. What it had was patience and courage. ASML believed that extreme ultraviolet lithography was not impossible. It was just unfinished. So they made a decision that would define the next 30 years. They would bet everything on it. They partnered with research labs. They worked with American scientists. They collaborated with Japanese mirror experts. They built supply chains across continents. They invested billions before making a single profitable machine. Year after year, they burned money. Competitors laughed. Investors worried. Executives questioned the strategy. But ASML kept going because they understood something fundamental. If EUV worked, whoever controlled it would control the future of computing. The first major breakthrough came with light generation. Making EUV light was the hardest problem. You could not use lamps. You could not use lasers directly. You could not use conventional sources. So engineers invented something new. They used tin, liquid metal tin. They fired microscopic droplets through a vacuum chamber. Each droplet was smaller than a cell. Each one moved at incredible speed. Then high-powered lasers hit the droplet once, twice, 3 times. The first pulse flattened it. The second heated it. The third turned it into plasma, a tiny exploding star. At that moment, it released extreme ultraviolet light for a fraction of a second at exactly the right wavelength, 50,000 times per second, every second. Perfectly synchronized, perfectly aligned, perfectly timed. If the timing was off by microseconds, everything failed. If the droplet mispositioned by microns, everything failed. If the laser lost power, everything failed. The system had to be flawless. Next came the mirrors. EUV light cannot be refracted. It cannot pass through lenses. It is absorbed by almost everything. So the entire optical system had to be reflective. No glass, no plastic, only mirrors. But not ordinary mirrors. Multi-layer mirrors. Dozens of layers of molybdenum and silicon. Each layer only atoms thick. Each layer precisely tuned. Each surface polished to atomic smoothness. They reflected about 70% of EUV light, which sounds good. Until you realize the light bounces multiple times. After 10 reflections, most of it is gone. So every mirror had to be perfect. Any defect meant failure. Manufacturing these mirrors took years. Only a few companies in the world could do it. Each mirror cost millions. Each one took months to produce. Each one was unique. Then came alignment. The machine had to position wafers, masks, and mirrors with insane precision. Nanometers, picometers, fractions of atoms. Vibrations from footsteps could ruin patterns. Temperature changes could distort frames. Air currents could shift components. So the machines were isolated, suspended, stabilized, encased, protected. They operated in near-perfect vacuum, with climate control down to fractions of degrees, with sensors everywhere, with computers constantly correcting errors. Then came software, thousands of control systems, millions of lines of code, monitoring lasers, droplets, mirrors, stages, motors, temperature, pressure, magnetic fields, everything, all in real time, all without interruption. Because if the system stopped, restarting took days, sometimes weeks. By the early 2000s, ASML had prototypes. They barely worked. They broke constantly. They produced low-quality chips. They were unreliable. Critics said, "We told you so." But ASML learned. They improved. They fixed. They redesigned again and again. They partnered with Intel, with TSMC, with Samsung, the biggest chip makers in the world. Together, they funded development. Together, they shared risk. Together, they pushed forward. Governments also stepped in. The United States realized this technology was strategic. So did Europe. So did Japan. So did China. EUV became geopolitics. Whoever controlled it controlled advanced computing. And advanced computing meant military power, economic power, artificial intelligence, surveillance, cybersecurity, space, medicine, everything. So governments protected ASML, restricted exports, controlled supply chains, limited access. By the 2010s, the first production machines appeared. They were enormous, the size of a bus, weighing hundreds of tons, containing more than 100,000 parts, shipped in dozens of crates, assembled on site, costing over $150 million, then $200 million, then $300 million, then $400 million each. Only a handful of companies could afford them. Each one became the heart of a factory. Without it, no advanced chips. With it, technological leadership. By 2018, EUV finally worked, not perfectly, not cheaply, but reliably. Moore's law was saved, not by magic, not by genius alone, but by decades of stubborn engineering. By international cooperation, by political support, by financial risk, by thousands of anonymous engineers, by millions of failed experiments, by billions of dollars, and by one company that refused to quit. ASML became the most important company nobody had heard of, more powerful than many tech giants. Because without its machines, none of them could move forward. The future of computing now ran through a factory in the Netherlands, and the race was not over. It was only beginning. By the time extreme ultraviolet machines became reliable, the world had changed. Computers were no longer just tools. They were becoming decision makers. They were learning, recognizing faces, predicting behavior, driving cars, writing text, designing drugs, simulating weather, training artificial intelligence. And all of it depended on chips, more powerful chips, denser chips, more efficient chips. Every generation mattered. Every nanometer mattered. Every improvement multiplied across billions of devices. So when ASML's machines unlocked the next step, governments took notice. The United States realized something uncomfortable. It did not control this technology. Europe did. One company, in one small country, had become the gatekeeper of the digital age. without ASML. No one could build the most advanced processors. Not Intel, not Apple, not Nvidia, not AMD, not Google, not Amazon, not the Pentagon, not NASA, not anyone. At the same time, China was racing forward, spending hundreds of billions, building fabs, training engineers, importing equipment, trying to close the gap, because whoever controlled advanced chips would control artificial intelligence. And whoever controlled artificial intelligence would shape the 21st century. Surveillance, weapons, economics, medicine, information, everything. So export controls appeared. Restrictions, blacklists, diplomacy, pressure. The US convinced Europe and Japan to limit access. ASML was forbidden from selling its most advanced machines to China, not because of business, because of strategy, because of power, because of fear. A single EUV machine could shift balances, could accelerate entire industries, could change military capabilities. So it became a geopolitical object. Piece of equipment guarded like a weapon. Meanwhile, chip makers pushed forward. They built factories costing tens of billions, cities of steel and glass, clean rooms larger than football fields, filled with robots and humans in white suits. Inside, EUV machines worked day and night, drawing patterns smaller than viruses, printing logic into silicon, turning mathematics into matter, turning theory into reality. But even EUV is not infinite. It has limits. Physics never stops pushing back. Wavelengths cannot shrink forever. Materials cannot remain perfect forever. Errors accumulate. Heat increases. Quantum effects appear. Electrons begin to tunnel. Signals blur. Noise rises. Engineers are already fighting the next wall. They stack chips vertically. They integrate memory and logic. They design new architectures. They explore new materials. They experiment with quantum computing, with neuromorphic chips, with photonics, with 3D integration. Because Moore's law, as it once existed, is over. What remains is something harder, more complex, more expensive, more fragile. Progress now comes from many directions, not just smaller transistors, but smarter design, better software, tighter integration, more specialization, and still, everything traces back to light, to mirrors, to droplets of tin, to lasers, to atomic smoothness, to decades of persistence. Every time you unlock your phone, every time you stream a movie, every time you ask an AI a question, you are using the result of this invisible struggle, a struggle fought in labs, in factories, in boardrooms, in government offices, across continents, across generations. Thousands of scientists who never became famous, engineers whose names you will never know, technicians who spent nights fixing machines, programmers who optimized systems, physicists who calculated impossible tolerances, all working toward one goal. Make things smaller, make things faster, make things better, not because it is easy, because civilization now depends on it. And there is a deeper lesson here. Progress does not happen in leaps. It happens in stubborn steps, in decades of failure, in ideas that sound foolish, in projects that lose money for years, in people who refuse to quit. Hiroki Kinoshita was dismissed, ignored, doubted. But he was right. ASML was criticized, mocked, questioned, but they persisted. Scientists in nuclear labs had no idea their work would power smartphones. Chip engineers never imagined shaping geopolitics. Mirror makers never thought their craft would decide AI races. Yet here we are. A world where a droplet of tin and a beam of light help determine global power. A world where atomic smoothness supports digital empires. A world where invisible machines shape visible reality. The future of computing will not be built by magic. It will be built the same way as always, by people who see limits and refuse to accept them, by engineers who turn theory into hardware, by scientists who push equations into reality, by societies willing to invest in knowledge, by generations willing to think long term. Moore's law was never really about transistors. It was about belief. Belief that tomorrow could be better than today, that complexity could be mastered, that precision could be achieved, that the impossible could become normal. And as long as that belief remains, progress will continue. Not forever, not without struggle, but long enough to reshape the world again and again and again.